Dear students, welcome to our next lesson on model-driven software engineering. This is lesson 4. The topic of our today's lecture is model-driven architecture. In this presentation, we are going to cover the following topics: model-driven engineering, model-driven architecture, types of models, problems tackled by MDA, importance of models, and model transformation. Model-driven engineering, or MDE, is an approach to software development whereby models, rather than programs, are the principal outputs of the development process. The programs that execute on a hardware or software platform are generated automatically from the models. Proponents of MDE argue that this raises the level of abstraction in software engineering, so that engineers no longer have to be concerned with programming language details or the specifics of execution platforms. Model-driven engineering was developed from the idea of model-driven architecture. This was proposed by the Object Management Group, or OMG, as a new software development paradigm. MDA focuses on the design and implementation stages of software development, whereas MDE is concerned with all aspects of the software engineering process. Therefore, topics such as model-based requirements engineering, software processes for model-based development, and model-based testing are part of MDE but are not considered in MDA. MDA, as an approach to system engineering, has been adopted by a number of large companies to support their development processes. Model-driven architecture is a model-focused approach to software design and implementation that uses a subset of UML models to describe a system. Here, models at different levels of abstraction are created. From a high-level platform-independent model, it is possible in principle to generate a working program without manual intervention. The MDA method recommends that 3 types of abstract system model should be produced. First, a computation-independent model, or CIM. CIMs model the important domain abstractions used in a system and so are sometimes called domain models. You may develop several different CIMs, reflecting different views of the system. For example, there may be a security CIM in which you identify important security abstractions, such as an asset and a role, and the patient record CIM in which you describe abstractions such as patients and consultations. Second, a platform-independent model, or PIM. PIMs model the operation of the system without reference to its implementation. A PIM is usually described using UML models that show the static system structure and how it responds to external and internal events. Third, platform-specific models, or PSM. PSMs are transformations of the platform-independent model with a separate PSM for each application platform. In principle, there may be layers of PSM, with each layer adding some platform-specific detail. So the first level PSM could be middleware-specific but database-independent. When a specific database has been chosen, a database-specific PSM can then be generated. Model-based engineering allows engineers to think about systems at a high level of abstraction without concern of the details of their implementation. This reduces the likelihood of errors, speeds up the design and implementation process, and allows for the creation of reusable, platform-independent application models. By using powerful tools, system implementations can be generated for different platforms from the same model. Therefore, to adapt the system to some new platform technology, you write a model translator for that platform. When this is available, all platform-independent models can then be rapidly rehosted on the new platform. Fundamental to MDA is the notion that transformations between models can be defined and applied automatically by software tools, as illustrated on this slide. This diagram also shows a final level of automatic transformation where a transformation is applied to the PSM to generate the executable code that will run on the designated software platform. Therefore, in principle at least, executable software can be generated from a high-level system model. In practice, completely automated translation of models to code is rarely possible. The translation of high-level SIM to PIM models remains a research problem, and for production systems, human intervention, illustrated on this slide using a stick figure, is normally required. A particularly difficult problem for automated model transformation is the need to link the concepts used in different SIMs. For example, the concept of a role in a security SIM that includes role-driven access control may have to be mapped onto the concept of a staff member in a hospital SIM. Only a person who understands both security and the hospital environment can make this mapping. The translation of platform-independent to platform-specific models is a simpler technical problem. Commercial tools and open-source tools are available that provide translators from PIMs to common platforms such as Java and J2EE. These use an extensive library of platform-specific rules and patterns to convert a PIM to PSM. There may be several PSMs for each PIM in the system. If a software system is intended to run on different platforms such as J2EE and .NET, for example, then in principle you only have to maintain a single PIM. The PSM for each platform are automatically generated as shown on this slide. Software development is often compared with hardware development in terms of maturity. While in hardware development there has been much progress, for example, processor speed has grown exponentially in 20 years, the progress made in software development seems to be minimal. To some extent, this is a matter of appearances. The progress made in software development cannot be measured in terms of development speed or costs. Progress in software development is evident from the fact that it is feasible to build much more complex and larger systems. Just think how quickly and efficiently we would be able to build a monolithic mainframe application that has no graphical user interface and no connections to other systems. We never do this anymore, and that is why we do not have solid figures to support the idea that progress has been made. Still, software development is an area in which we are struggling with a number of major problems. Writing software is labor-intensive. With each new technology, much work needs to be done again and again. Systems are never built using only one technology, and systems always need to communicate with other systems. There is always the problem of continuously changing requirements. In MDA, the focus for a developer shifts to the development of a PIM. The PSMs that are needed are generated by transformation from PIM to PSM. Of course, someone still needs to define the exact transformation, which is a difficult and specialized task. But such a transformation only needs to be defined once, and can then be applied in the development of many systems. The payback for the effort to define a transformation is large, but it can only be done by highly skilled people. The majority of developers will focus on the development of PIMs, since they can work independently of details and specifics of the target platforms. There is a lot of technical detail that they do not need to bother with. These technical details will be automatically added by the PIM to PSM transformation. This improves the productivity in two ways. In the first place, the PIM developers have less work to do because platform-specific details need not be designed and written down. They are already addressed in the transformation definition. At the PSM and code level, there is much less code to be written, because a large amount of the code is already generated from the PIM. The second transformation comes from the fact that the developers can shift focus from code to PIM, thus paying more attention to solving the business problem at hand. This results in a system that fits much better with the needs of the end users. The end users get better functionality in less time. Such a productivity gain can only be reached by the use of tools that fully automate the generation of a PSM from a PIM. Note that this implies that much of the information about the application must be incorporated in the PIM and/or the generation tool. Because the high-level model is no longer just paper, but directly related to the generated code, the demands on the completeness and consistency of the high-level model are higher than in traditional development. A human reading a paper model may be forgiving, an automated transformation tool is not. Within the MDA, portability is achieved by focusing on the development of PIMs, which are by definition platform independent. The same PIM can be automatically transformed into multiple PSMs for different platforms. Despite the fact that there is a tremendous number of new technologies developed, everything you specify at the PIM level is therefore completely portable. Since new technologies appear, we all have to follow them due to such reasons as customers' demand, new technologies solve problems that were difficult to tackle, and of course, tool vendors no longer support the old technologies. The extent to which portability can be achieved depends on the automated transformation tools that are available. For popular platforms, a large number of tools will undoubtedly be or become available. For less popular platforms, you may have to use a tool that supports plug-in transformation definitions and write the transformation definition yourself. For new technologies and platforms that will arrive in the future, the software industry needs to deliver the corresponding transformations in time. This enables us to quickly deploy new systems with new technology based on our old and existing PIMs. As systems evolve, they undergo updates and changes. These changes involve using new technologies along with old ones. These technologies of different generations need to talk with each other. As monolithic systems are highly ineffective in today's world, there have to be different components within one system that must communicate as prescribed by its functionality. Multiple PSMs generated from one PIM may have relationships. In MDA, these are called bridges. When PSMs are targeted at different platforms, they cannot directly talk with each other. One way or another, we need to transform concepts from one platform into concepts used in another platform. This is what interoperability is all about. MDA addresses this problem by generating not only the PSMs but the necessary bridges between them as well. To picture the overall interoperability idea, please look at this picture. If you are able to transform one PIM into two PSMs targeted at two platforms, all of the information we need to bridge the gap between the two PSMs is available. For each element in one PSM, we know from which element in the PIM it has been transformed. From the PIM element, we know what the corresponding element is in the second PSM. We can therefore deduce how elements from one PSM relate to elements in the second PSM. Since we also know all of the platform-specific technical details of both PSMs, we have all the information we need to generate a bridge between the two PSMs. Take, for example, one PSM to be a Java model and the other PSM to be a relational database model. From an element customer, in the PIM, we know to which Java class or classes this is transformed. We also know to which table or tables this customer element is transformed. Building a bridge between a Java object and the Java PSM and the table in the relational PSM is easy. To retrieve an object from the database, we query the table or tables transformed from customer and instantiate the class or classes in the other PSM with the data. To store an object, we find the data in the Java object and store it in the customer tables. Cross-platform interoperability can be realized by tools that not only generate PSMs, but the bridges between them, and possibly to other platforms as well. We can survive technology changes while preserving your investment in the PIM. Working with the MDA lifecycle, developers can focus on the PIM, which is at a higher level of abstraction than code. The PIM is used to generate the PSM, which in turn is used to generate the code. The model is an exact representation of the code. Thus, the PIM fulfills the function of high-level documentation that is needed for any software system. The big difference is that the PIM is not abandoned after writing. Changes made to the system will eventually be made by changing the PIM and regenerating the PSM and the code. In practice today, many of the changes are made to the PSM and code is generated from these. Good tools, however, will be able to maintain the relationship between PIM and PSM even when changes to the PSM are made. Changes in the PSM will thus be reflected in the PIM, and high-level documentation will remain consistent with the actual code. In the MDA approach, the documentation at a higher level of abstraction will naturally be available. Even at that level, the need to write down additional information which cannot be captured in a PIM will remain. This includes, for example, argumentation for choices that have been made while developing the PIM. Let us formulate the following definitions. Model-driven engineering, or MDE, is a methodology for software development which rests on the approach of creating and using models of some domain and reasoning about their general concepts rather than developing codes. Model-driven architecture, or MDA, is an approach to software design and development which is based on the principles of MDE. The name MDA stresses the fact that models are the focal point of MDA. The models we take into account are models that are relevant to developing software. Note that this includes more than just models of software. When a piece of software is meant to support a business, the business model is relevant as well. But what exactly do we mean when we use the word model? To come up with a definition that is both general enough to fit many different types of models is difficult. The definition also needs to be specific enough to help us specify automatic transformation of one model into another. A model describes a system in such a way that it can be used to produce a similar system. The new system is not equal to the old one because a model abstracts away from the details of the system. Therefore, details in both old and new system might differ. Yet, because only the details are omitted in the model and the main characteristics remain, the newly produced system has the same main characteristics as the original. That is, it is similar to it. The more detailed the model is, the more similar the systems it describes will be. A model is always written in a language. This might be UML, plain English, a programming language, or any other language we can think of. To enable automatic transformation of a model, we need to restrict the models suitable for MDA to models that are written in a well-defined language. A well-defined language has a well-defined form and meaning that can be interpreted automatically by a computer. We consider natural languages as not being well-defined because they cannot be interpreted by computers. Therefore, they are not suitable for automatic transformation within the MDA framework. From this point onward, we use the following definitions. A model is a description of or part of a system written in a well-defined language. A well-defined language is a language with well-defined form or syntax and meaning or semantics, which is suitable for automated interpretation by a computer. Note that although many of the example models in this book are written in UML, MDA is certainly not restricted to UML. The only restriction is that the models must be written in a language that is well-defined. Our definition intentionally includes source code as a model of the software. Source code is written in a well-formed language. The programming language can be understood by a compiler and it describes a system. It is of course a highly platform-specific model but a model nevertheless. This picture shows the relationship between the model, the system it describes, and the language in which it is written. The system described by a business model is a business or a company. Languages that are used for business modeling contain a vocabulary that allows the modeler to specify business processes, stakeholders, departments, dependencies between processes, and so on. A business model does not necessarily say anything about the software system used within the company. Therefore, it is also called a computational independent model, or a SIM. Whenever a part of the business is supported by a software system, a specific software model for that system is written. This software model is a description of the software system. Business and software systems describe quite different categories of systems in the real world. Still, the requirements of the software system are derived from the business model that the software needs to support. For most business models, there are multiple software systems with different software models. Each software system is used to support a different piece of one business model. So there is a relationship between the business model and the software models that describe the software supporting the business as shown on this slide. We have seen that the type of the system described by a model is relevant for model transformations. A SIM is a software-independent model used to describe a business system. Certain parts of a SIM may be supported by software systems, but the SIM itself remains software-independent. Automatic derivation of PIMs from a SIM is not possible, because the choices of what pieces of a SIM are to be supported by a software system are always human. For each system supporting part of a SIM, a PIM needs to be developed first. Many people talk about structural models versus dynamic models. In UML, for example, the class diagram is called a structural model and the state diagram a dynamic model, while in reality the class diagram and state diagram are so dependent on each other that they must be regarded as part of the same model. The fact that we start software modeling by drawing classes in a class diagram does not mean we are developing a class model. We are developing a software model by defining static aspects through a static view. If we start our development by drawing a dynamic diagram like the state or sequence diagram, we are developing a software model by defining dynamic aspects through a dynamic view. Later, when we add a state diagram to our class diagram or a class diagram to our state diagram, we are merely adding dynamic aspects through a dynamic view to the same model, or vice versa. Therefore, the common terminology is a bit sloppy. The class and state diagrams could better be called structural and dynamic views. This picture shows how different diagrams in UML are all views on the same model. They are all written in the same language, which is UML. In UML, the relationship between dynamic and static views is direct, because they show different visualizations of the same thing in the same model. For example, a class in a UML model is shown as a rectangle with the class name in a class view, while it is shown as the type of an instance in a sequence diagram. The same class can be the anchoring point for a complete state diagram. All the diagrams are views on the same class. If a system has both structural and dynamic aspects and the language used is able to express both structural and dynamic aspects, the model of the system contains both aspects. Therefore, a UML model of a system includes both the structural and the dynamic aspects shown in different diagrams. If structural and dynamic aspects cannot be described in one model because the language used is not able to express certain aspects, then there are indeed two models. Note that both models are related. They describe the same system. The type of the model is, in such a case, more clearly described by naming the language in which it is written than by the use of the connotation, like structural or dynamic. For example, an entity relationship model or PetriNet model. This picture shows a situation where two different models describing the same system are written in two different languages. We can conclude with the observation that the aspect that is described in a diagram or model that is structural or dynamic is not relevant for the type of a model. The essential characteristic of a model is the language in which the model is written. Some languages are more expressive than others, and more suitable for representing certain aspects of a system. On this slide, you can see that in comparison with the traditional software lifecycle, MDA approach develops its artifacts, SIEM, PIM, PSM, and code as a result of the respective activities, requirements, analysis, design, coding, and testing. One important remark has to be made at this point is that MDA approach feeds back the changes to the software and computer programs, right to the initial stage of developing PIM, which is analysis, and these changes are introduced along the whole cycle by virtue of implementing automatic or semi-automatic transformations. A computation-independent model represents the most abstract model of some business. It can be written using some natural language like English. The SIEM is written using high-level specifications of business processes, including dependencies, stakeholders, departments, and so on. It does not at all mention anything about the software system. However, it does describe a business system in general terms. A platform-independent model, or PIM, is a model of a software system or business system that is independent of the specific technological platform used to implement it. A SIEM to PIM transformation is usually not automatic. This means that there is no machine-readable function that could map these two artifacts. Therefore, SIEM to PIM transformation are usually performed manually by human. However, there are several attempts in the current state of the art of MDA to automate or partially at least automate this transformation by developing a machine-readable high-level mapping function. A platform-specific model is a model of a software or business system that is linked to a specific technological platform. For example, a specific programming language, operating system, document file format, or a database. Platform-specific models are indispensable for the actual implementation of a system. One can also generate several PSMs from one PIM if there is a need for more than one platforms, so that for each platform a separate PSM is generated. This part of the transformation is often the most complex part in the MDA software development process, which is mostly performed by technical experts with minor or no contribution from the clients. The next and the final stage in software development is code generation from PSM. This step of the transformation is relatively easier and straightforward in so much as the knowledge about the technology is pre-specified in a greater detail in the PSM system models. The productivity increases by concentrating more on PIM or even SIEM development without bothering about the technical platform-specific details because they are already addressed in the transformation definition. Similarly, PSM and code level contain respective definitions for code generation. Therefore, developers will be able to shift their focus from coding to defining PIMs, thereby concentrating more on design issues and solving design-related problems, which will finally result in a system that fits better with the needs of the end users. Providing for transformation from one PIM to several PSMs, MDA solves the portability problem. Since PIM is a platform-independent model, it can be designed in a way to allow for generation of more than one PSMs. Generating more than one PSMs from a PIM assumes a generation of so-called bridges that would allow for these PSMs to communicate. When implementing a transformation, we specify how one element in the PIM is mapped to another element in the PSM. The same goes for the second PSM and its corresponding element in the PIM. Therefore, we can deduce how one element of the first PSM is related to another element of the second PSM. This property is referred to as interoperability. Because PIM is transformed to PSM or PSMs and PSM or PSMs to code, PIM model becomes an exact representation of the code. In the case where changes have to be introduced, usually these changes are done at the PSM level. The transformation tool has to reflect these changes in the PIM, therefore making the PIM consistent with the actual code. Therefore, the PIM can be considered as a high-level documentation necessary for any software system. In the broader picture, you can see that for performing a transformation, we have to develop transformation tools. These tools use the structure and entities of the PIM and transform them to the respective structure and entities of the PSM or PSMs. The same is done at the PSM to code transformation leg. In our assignment for this course, you will have to develop such a transformation tool from PIM to PSM using one of the famous object-oriented programming language for such purposes called KERMETA, which stands for Kernel Metamodeling. Today, we have covered the basic foundation of MDA, model-driven engineering, its philosophy, types of models, or we also call them artifacts, and we emphasized their importance. We briefly defined the term transformation. We also described what problems MDA solves and explained why and why not the transformations can be automatic. I'll see you on the next class. Thank you very much.